Hi, everybody. I wish I were in Kiel, but it's simply not a possibility right now. What I'd like to talk about today is more deterministic software for cyber-physical systems, and there's quite a number of people who are there in Kiel who have had a lot of influence on my thinking in this, as well as other people around the world. And the work that I'm going to talk about specifically today is centered around a project that my group is very much focused on, and it's being pursued collaboratively, primarily with people in Germany at TU Dresden and in Kiel. And that's a project that we call lingua franca. And so I'm going to try to give some motivation. And Martin Lostra gave a talk earlier, which was in the middle of the night for me, that described some of the core concepts in lingua franca, particularly the use of a multiplicity of timelines, which I think is a unique feature of this language. And so I'd like to try to motivate that and step back and look at the big picture and how did we come to this design and why it is the way it is. So the context of my work is on cyber-physical systems. Cyber-physical systems, I think probably everybody here knows what we're talking about, but the intrinsic features are that there is some physical subsystem that is an intrinsic part of the design. It's not just something that you communicate with external from the design. And there's typically more than one computational platform, and there's a network fabric that is used to communicate between these computational platforms. And it can involve some mix of cloud computing, some local computing, some edge computing. And the challenges are integrating these complex subsystems and getting adequate reliability, repeatability, and testability. And in particular, the interaction with the physical world is what makes these systems particularly vulnerable to safety issues, for example. So I'd like to start with a disturbingly simple challenge problem that seems to have no good solution today. So the problem here is to automate the opening of an aircraft door. And just to make this as simple as possible, I'm not even going to worry about closing the aircraft door. It's just opening, right? And our challenge is to build a software service that's going to run on a microprocessor in the door, and it'll communicate over the network with other subsystems in the aircraft. And it provides two services, open and disarm. And the disarm service is an important service because when the aircraft is in motion or flying, the door is armed, which means that if it is opened, emergency escape slides will be deployed. And they deploy rather rapidly, and so you really don't want them to deploy at the wrong time. So this microprocessor is going to listen on the network for open and disarm messages. And my challenge problem is exceedingly simple. What should the software in this microprocessor do when it receives a message to open the door? Right? What could be simpler in a cyber-physical system design than designing the software to do this? This turns out to be a rather difficult question to answer because you don't have typically any assurance that disarm messages and open messages are received in the right order. And so you're not really sure whether there's been a disarm message that has been launched into the network before the open message was launched into the network. All you know at this point is that you're seeing an open message. And if you open the door without disarming it ahead of time, this can be disastrous. It's a safety critical situation. People could get killed. So the question remains, what should you do? So let's look at what a possible architecture might look like. So you might have, for example, an embedded vision system that is put in for safety purposes that performs the function that today is realized with a natural intelligence. So we're going to replace this natural intelligence with an artificial intelligence. So today in an aircraft, a flight attendant looks out the window. The doors always have windows for this purpose to verify that there is in fact a ramp outside the door before the flight attendant disarms the door. Okay, the flight attendant is required to verify that there is in fact a ramp. If there is no ramp, the flight attendant is not permitted to disarm the door. So we're going to do this with an embedded vision system that will detect whenever there's a ramp adjacent to the door, it will issue a disarm message. And of course, you could get also controls signals coming from a cockpit control where the pilot might say disarm doors for arrival. And today they do that verbally to communicate with the natural intelligence, but perhaps the pilot could do it by simply throwing a switch and then could open the door. And you might also have a fire detection system on the aircraft that if the back of the aircraft is on fire, it issues an open message and all the doors open whether they're armed or not. Okay? So the door controller now has the potential to receive disarm messages and open messages. Now, how should we design the network fabric? Well, there's a number of very popular techniques today. And so one of them is publish and subscribe. This is actually used quite commonly in robotics systems. It's the core of ROS, the robot operating system from Willow Garage. And in ROS, this publish and subscribe fabric is simply that, disarm and open are topics, and the software components post to these topics, and the door controller listens for these topics. There's also MQTT, which is very widely used in IoT applications, which are also cyber-physical system applications. And then there's cloud-based infrastructures like Azure and Google Cloud that use publish and subscribe as well. Or you might use a message passing scheme. So message passing schemes are fairly widespread. They're used in Erlang, for example, for embedded systems, in UML-RT for real-time systems. Akka and Ray are used more in enterprise computing and cloud-based applications. There's also service-oriented architectures, which are essentially remote procedure calls. So Google's gRPC and Thrift are good examples of that. And somewhat less widely used, but still, there's a track record or some shared memory architecture schemas that are used as well. So the interesting thing about all of these is that they actually provide no assurance about the order of arrival of messages. The publish and subscribe fabric of ROS is completely non-deterministic with respect to this behavior. And ROS2 actually uses a more sophisticated networking infrastructure that allows messages to be prioritized. But these priorities are actually still best effort priorities. And so as a consequence, this can result actually in a masking of conceptual bugs in the system where messages arriving out of order simply becomes rare because you've chosen your priorities carefully, but it doesn't get eliminated semantically. So the question remains, what should the door controller do when it receives an open message? So one possible solution, of course, is just open the door. So how much should you test this? How much formal verification should you do? How do you constrain the design of other components? How do you constrain the network? In certain applications, like in avionics, for example, in the avionics world, they don't really use commodity networks. And so you actually have a lot of control over the network, and it could be a perfectly reasonable design choice to actually regulate the order in which messages are transported over the network. But now the design of the door controller system becomes very tightly integrated with the design of the network. And so it's not necessarily a very modular design approach. And if you're trying to do this over commodity networks, you're doing Ethernet with TCP/IP, for example, in some factory automation application, this is going to be a lot more difficult to do. So another alternative to just opening the door would be to develop a distributed consensus. So you could respond by saying, well, wait a minute, I don't want to open the door if it's armed because that could be a safety critical situation. Let me make sure that the other components in the system are actually okay with me opening the door. So I send out a message saying, I've just gotten a request to open the door, but the door is armed. Any objections to opening the door? And then you wait for some responses. But the problem is that, remember that one of the subsystems was a fire detection system. And so you want to open the door if there's been a major disaster on the plane so that the passengers can escape. And many of the subsystems may have failed, so you may not, in fact, get responses. So in order to design this software component this way, you're going to have to go and read all of Leslie Lamport's papers, which are going to tell you, among other things, what the impossibility, there's a variety of impossibility proofs about developing distributed consensus in the face of certain numbers of faults. And what seemed like a rather trivial software design problem has now become a potential PhD thesis topic. So another alternative, which is a very pragmatic one, is if you receive an open message, you just wait a while and then open the door. And the principle there is that if a disarm message has been sent by some other component, then presumably you will receive it after a certain amount of time. And so you just wait a little while, and if you don't receive a disarm message, you assume that one wasn't sent. But now the question is, how long should you wait, and how do you test the system, and more importantly, how do you justify it to the certification bodies? How do you say, well, I decided that 10 milliseconds was the right amount of time to wait? Well, what's the basis for that decision? So these are not very attractive solutions, any of the three. So let's pick particularly on one of the families of approaches to solving this problem, which is message passing schemas based on actors. So the original Hewitt and Aga actors, developed by Carl Hewitt in the 1970s and then really developed and formalized by Gul Aga, have this sort of architecture where there's a message queue that can receive messages from any number of sources, and then the messages get handled in first in, first out order by handlers that can be message specific, which will then send out messages to other actors. And the real problem here is that the messages are handled in first out order, and consequently there's not really any semantics to this unless the network itself provides some ordering on the message arrivals. Now, this is not necessarily a critical problem because sometimes the network does provide some semantics about ordering. So consider a very simple architecture here where you have a source actor. This is written in a slightly simplified version of Ray, which is one of the popular actor-oriented languages. So the source actor has a handler called main that creates a new instance of the door actor and then sends it a disarm message and then following that sends it an open door message. Now, if you assume that the communication between the source and the door is through a TCP socket, then you are actually assured that the disarm handler will be invoked before the door handler will be invoked, because TCP guarantees eventual delivery in order of message packets. Okay, so just using the semantics of TCP, you get an assurance that disarming the door will in fact occur before the opening of the door. But now let's just elaborate the architecture ever so slightly. So suppose that when we issue the disarm message, we want to route that through the embedded vision system that will check to see that there is in fact a ramp outside the door, and will pass the disarm message on only if it verifies that there is a ramp outside the door. So here's a simplified version of that. And in this particular case, the pass disarm actor doesn't do any checking, it just forwards the message. So it's about as close as you can get to a no-op in an actor-oriented framework. It just receives an input message and then sends an output message. Okay? But now, there are no reasonable assumptions about the network that are sufficient to guarantee that the disarm message will be handled before the door message, before the open door message is handled. If TCP will not be sufficient because there's three different communication channels here, and if each of them is implemented with a TCP socket, there's not going to be any assurance about the relative ordering of messages across the TCP sockets. TCP only ensures message ordering within a particular socket. So this is disheartening because this is an extremely simple architecture, and yet we have a very serious safety problem that is intrinsic to the problem. So some possible solutions. Well, I mean, a common one is you just ignore the problem. And you test it a lot, and as long as it works it works reliably in testing, then you ship it. That's unfortunately a very common solution to these kinds of problems. A more sophisticated thing to do would be to model the timing. So if you know enough about your network fabric, for example, instead of just assuming that it's Ross's publish and subscribe, you make some additional assumptions about message priorities and things like that. And you try to model the timing, and you try to guarantee that, in fact, the messages will arrive in the order so that they get handled correctly. But this could really be a very challenging problem, and it makes for a brittle design, because then any change in the network design, the addition of new components, for example, means that you have to completely redo the modeling and re-verify your entire system. So the third approach, which is the one that I'm going to advocate here, is to change the model of computation. So essentially, the model of computation needs to affect the network fabric and the way that network communication occurs. And there's actually a long history of techniques that can be used. And basically, the four families of techniques that I've used here are all about giving distributed and concurrent software deterministic behavior. So it is possible to have concurrent software that has deterministic behavior. There's a long history of techniques that do this. Data flow models do this, con-process networks, which date back to the 1970s, synchronous reactive languages, which date back to the early 1980s, and discrete event systems. And my current favorite these days is discrete event systems. And Stephen Edwards gave a very nice talk that also was about discrete event systems, and he used a term that I like a lot, which is sparse synchronous models. So in fact, the flavor of discrete event systems that we adopt is what Stephen calls a sparse synchronous system, in that at each instant in logical time, it has synchronous semantics, and then logical time advances, and at each logical time you have a sparse occurrence of events. So some subsystem some subcomponents in your system will react to events, and others will just remain dormant at those particular ticks. So you've seen this model before. So how does this translate into a solution to this aircraft door problem? Well, it turns out it's a little bit subtle, and it requires a lot more work in the infrastructure, but a lot less work in the application, which is, I think, the trade-off that we want to be looking for. So in particular, suppose that the embedded fission system issues a disarm message, and the fire detection system issues an open message. In a discrete event solution, these two messages acquire timestamps. So the disarm message has timestamp T1, the open message has timestamp T2. And the definition of correct behavior is now entirely dependent on the order of these two timestamps. So if the two timestamps are numerically identical, then they will occur at a common tick of the synchronous model. If they are different, then they will occur at separate ticks, and one of them will occur at an earlier tick, and one of them will occur at a later tick, and the one that occurs at the earlier tick will be handled earlier. So the numerical order of the timestamps is what determines the order of the processing of these events. And one of the very nice features of this approach to design is that we now have a very clear definition of what the program should do, what is the logic of the program, and we also have a very clear definition of what it means to correctly execute the program. A correct execution of the program that is based on these timestamps is an execution that respects the requirement that events be handled in timestamp order. And any execution that does not have that property is a faulty execution. So this makes it rather easy to design the door controller software, right? You just wait for incoming timestamp messages, and if you receive an open message and there is no disarm message, you open the door. It's that simple, okay? And as long as the infrastructure guarantees that you will be delivered messages in timestamp order, you will get correct execution. So this model of computation is not new. It's been around for a very long time, since the 1960s. It's been widely used primarily in simulation and in hardware design. It's the mechanism underlying most hardware design languages, like Verilog and VHDL and System C. And it's used very commonly for simulating networks. NS2 and NS3 are discrete event simulators of networks. OpNet is the discrete event simulator for networks. And it's used for simulating a lot of kinds of complex systems. And there's many books out there that you can find about this technique, and many pieces of software infrastructure, but almost all of them are about simulation. And what we're proposing here is not using this as a simulation tool, but using it as a deployment tool. It's the semantics of a deployment in a real implementation of a cyber-physical system. The interesting question about this is that the basic requirement in a discrete event system is that messages be handled in timestamp order. And how do you handle messages in timestamp order in a distributed system? So in particular, you've got two microprocessors separated in time, and they each have timestamped messages. And when can they handle those messages, and how can they be assured that they will not later see messages with earlier timestamps? So that's really the essential challenge, is how do you distribute this? How do you realize this in distributed machines? It turns out that that's also not a new problem. The distributed execution of discrete event simulators has been around for a long time, since the 1970s, because performance problems have been an issue with discrete event simulations. They're designed to simulate large, complex systems, so they want to be able to exploit distributed computation and parallel computation. Now, I'd like to give you an existence proof that distributed execution of discrete event models can be done efficiently at very large scales. I mean, by very large scale here, I mean global scales with millions of events being handled per second even, okay? So the existence proof that I'd like to give you is Google Spanner. So Google Spanner is a distributed database that was the first paper describing this work appeared in 2011, and it uses a distributed discrete event semantics. So the way Google Spanner works is that it's designed to give a database that has very high robustness. So even if an entire data center goes down, the database continues operating. So each data center will have replicated the data of the database. So it's a replicated database. This map shows data centers across the US that Google maintains, where they run Spanner as part of the infrastructure. And the way that the database works is that if you get a query coming in Seattle that says, for example, to update a record in the database. So suppose, for example, that the database is handling an airline reservation system, and Seattle is running a web server, and a query comes in saying, I want to reserve seat 7A of this flight, okay? Then what the Seattle data center will do is timestamp that query with a timestamp T. Now suppose that around the same time, another query comes into Dallas, and the query in Dallas just is asking, is this seat 7A of this flight available, okay? So the data center in Dallas will again timestamp the query with the timestamp R, and the question now becomes, what should Dallas respond? Is the data seat available or not? Okay? And the semantics of the database depends on the numerical relationship between T and R. Now, you can see that this is now a potentially challenging problem for the infrastructure to implement, because T is a number, R is a number. But T is in Seattle and R is in Dallas. So how do you compare two numbers that are physically separated by 1,500 miles? So one way to do it would be to develop a distributed consensus. So both data centers broadcast a message saying, I have a query with timestamp, whatever it is, can I respond to it? But that would be ridiculous, because then, you know, the technique will not scale. You'll be overwhelming the network with these broadcast messages constantly. And that's not going to be the solution, and that's certainly not the solution that Google Spanner uses. So the solution that Google Spanner uses, I can illustrate for you by taking just a simplified version of this particular problem. Okay, so here, assume that Seattle is running a web server, and it gets a query to reserve the seat on the airplane. So the actor that implements the web server sends a message to an actor that implements the database. And the message says, please update seat 7A to mark it as occupied. And the infrastructure timestamps that message based on a local clock, actually. So it assigns the local clock time to that timestamp, to that message. The database now says, okay, I've gotten a query that wants me to update the database. Now, when you update a database record, you do have to communicate with all the other clones of the database, because they need to update their records too. So Seattle will send out a message saying, I've got a request to update a record to mark this seat as occupied. And as a consequence, this timestamped message with timestamp T will be sent over the network, and through a network interface will ultimately get to this clone of the database here in Dallas. Okay? Around the same time, the web server in Dallas receives a query, is the seat available, and it timestamps that using its local clock with timestamp R. And now the correct response for this database component is simply based on the numerical value between these two timestamps. If R is less than T, then the database will respond that the seat's available. Okay, so the question is, how do we do that, right? Because the problem is that the message timestamped with R may arrive well before you see the message timestamped with T. The message timestamped with T is coming from Seattle, and who knows when that's going to arrive. So one solution is, in fact, you just wait for it to arrive, okay? So you wait for messages to come from Seattle before you issue a response. So this is an old technique. It's called the Chandy and Misra technique. It was published by Chandy and Misra in 1979. It makes certain assumptions about the network fabric, but they're practical, realizable assumptions. So it assumes that each communication channel communicates events reliably in timestamp order. So the semantics of Chandy and Misra is very simple. The database component here in Dallas has two input ports, and it simply waits until it has a message on the top channel and a message on the bottom channel. And now, because of the assumption that every channel communicates messages reliably in timestamp order, it can simply compare these two timestamps and handle the one that is the lesser timestamp. So if the lesser timestamp is R1, it will reply the seat's available. Okay? Now, the problem with this, of course, is that there may be no message from Seattle. Maybe nobody's trying to reserve this seat. So Chandy and Misra anticipated this problem, and they said, well, Seattle has to send null messages, and it has to send these frequently enough to meet whatever requirements you have for throughput on this system. So for example, if my requirement is that the web server must respond within 30 milliseconds, then Seattle is going to have to at least send messages once every 30 milliseconds, and these messages essentially are saying, I don't have anything to say, and my timestamp is such. And now the system can make progress, but the network gets flooded with these timestamped null messages. So it's not very efficient. There's a lot of network traffic that gets created. But a worse problem for cyber-physical systems is that every node in the system now becomes a single point of failure. If the data center in Seattle goes down, it stops sending messages, and no other database clone can issue any responses at all because it's not getting any messages from Seattle. So that's not going to be an acceptable solution for a cyber-physical system design. We could try a different approach, which was introduced in the 1980s by Jefferson. Jefferson called it time warp, and many people call it optimistic computation, which is where if Dallas receives a query and assigns it timestamp R, it simply responds speculatively saying, yeah, the seat's available, no problem. And then if it later receives a message from Seattle with an earlier timestamp, it retracts the previous reply and says, oops, I didn't mean the seat was available. Pretend I never said that, and let me backtrack to an earlier state and re-execute the processing of all of the events. But of course, the problem here is that you can't backtrack an interaction with the physical world. If you've issued a reply saying that the seat is available, some web page somewhere has indicated that the seat's available, and you can't backtrack the impression in the user's eyes. And of course, in the kind of cyber-physical systems that I'm interested in, industrial automation, in the case of the door controller for the aircraft, you opened the door and the slides deployed. And now you say, oops, I didn't mean to open the door. Can you reverse that and undeploy the slides? There is no undeploying of these slides. Okay, once these slides are just deployed, they are trash, actually, and they get removed from the aircraft and replaced with new slides. So there is no backtracking of the physical actions and the physical side effects of the software, and so this technique doesn't really work very well in cyber-physical systems. It does have the nice property that there's no single point of failure and that you can process events without any network traffic. But there's actually considerable overhead because you have to snapshot the state of your system periodically, and you have uncontrollable latencies because anytime a backtrack occurs, you have to revert your state to the most recent snapshot and then process all of the events, timestamped events that have occurred since that snapshot. And this can introduce very large latencies and quite a lot of computation that is triggered by a backtracking event. So this solution is not very attractive for cyber-physical systems either. So you could use another technique, which has been realized in the high-level architecture, which was introduced starting in the 1990s, where you have a centralized controller called the Runtime Infrastructure. And the way that this works is simply that whenever a component in your system wants to advance its logical time to some timestamp r, it makes a query to the runtime infrastructure saying, I would like to request to advance my time to r, my logical time to r. And each component is making such requests, and the runtime infrastructure consolidates these requests, finds the least logical time that all of the components are requesting an advance to, and then issues a time advance grant to all of the components to advance time to that logical time. But this, again, is not very attractive for this application because the RTI is a single point of failure. Actually, every component is a single point of failure, again, because any component that doesn't give us an update about its next event request time will block the advancement of time for all of the other components. So this works well for simulation, but again, not for cyber-physical systems and not for online deployment. And clearly, none of these three techniques is what Google Spanner does. So the Spanner approach, which was a reinvention of a technique that my group had introduced 5 years earlier that we called TIDES, is really conceptually very simple. And it's the same as the sort of ad hoc solution that I had to the door opening problem, which is you wait a while and then you open the door. But it gives an answer to the question of how long you wait. And the answer is very specifically, the event in Dallas with timestamp r is safe to process when the clock in Dallas exceeds r plus w plus l plus e. W plus L plus E are three numbers that are calculated ahead of time and are known to Dallas. And so when Dallas receives a query, it just watches its local clock, and then when it hits a threshold, it replies. Okay? So how does this work? Well, first, it makes the assumption that there is a local real-time clock on each platform, and that the timestamps are drawn from those local clocks. Okay? So when a timestamp R is assigned to the web server's query, it's drawn from the local clock. That's very practical. Notice that, there's a lot of formalisms out there that just assume there's a timestamp R drawn from Newtonian time. But Newtonian time is not accessible. It's not available to you. It's an abstraction invented by Isaac Newton that doesn't actually exist in the physical world. In fact, we know it's now a flawed model of time from the theory of relativity. And it's not a realistic assumption to just say that this is the time at which the query occurred. So that's not the assumption made here. The assumption made here is that timestamp is drawn from a local measurement of real time. And that's a very realizable assumption. Okay. We assume that the database component has a bound on its execution time. So it takes it a bounded amount of time to issue the message to the network. And we assume that there's a bound on the network latency, L, which is the amount of time that it will take that message to be received in Seattle. And then we can observe that this message with timestamp T will be known in Dallas at platform B by the time T plus W plus L. But T plus W plus L is the time at Seattle's clock, not at Dallas's clock. Okay? And Dallas doesn't have access to Seattle's clock. So we need to make an additional assumption, which is that there's a bound on the clock synchronization error. So this could be accomplished, for example, by synchronizing these clocks to GPS, which gives you about 100 nanoseconds bound on the clock synchronization error. Or it could use an even more precise technique like the IEEE 1588 standard, which is actually used in Spanner, to synchronize these clocks to even tighter tolerances than you can get from GPS. And it's also more robust than a synchronization to GPS, because GPS can be jammed and spoofed fairly easily. So we assume a bound on the clock synchronization error, and then we simply observe that this event with timestamp T will be known in Dallas by time T plus W plus L plus E by the clock at Dallas. Okay? This is a practical thing. We can now compare that number. W plus L plus E is a number that we simply need to add to the timestamp that we would like to advance to. Okay, and then when our local clock reaches that timestamp, it is safe because under these assumptions, we will have seen all messages that have earlier timestamps. Okay, so that's the principle behind Spanner, and it's a very nice model. Okay, it has a lot of very nice features. There is no single point of failure. Seattle can go down completely, offline, shut down the database, complete power failure, earthquake happened, volcano got it, anything, no problem. Dallas keeps responding. Dallas can respond to the network query with no network traffic. In fact, in Spanner, network traffic is generated only by updates to the database, not by queries to the value of the database. A query to the value of the database, the data center just has to watch its local clock and then it responds with its local copy. Okay, so network traffic gets drastically reduced compared to distributed consensus schemas. The latencies are well defined, right? So suppose that there's an engineering requirement that you need the Dallas data center to respond within 30 milliseconds to any query about, the airline seat. That 30 milliseconds becomes a requirement for W plus L plus E. You now have to design your system so that the sum of the execution time bound of your database, the assumed bound on your network latency, and your clock synchronization error doesn't exceed 30 milliseconds. So that becomes a requirement. You can design your system so that that's the case. Okay, it enables you to pick your networking technology, pick your clock synchronization technology, do your worst case execution time analysis for your software, for the particular pieces of software that matters. So it turns this into a very nice engineering problem. The time thresholds are computed statically. They're based on the connection topology. Now, the connection topology can change over time, but it changes at logical times. So the changes themselves occur at particular timestamps. And so you can actually tolerate changes in topology and then recompute these thresholds when those changes occur. But the most interesting feature to me is that the assumptions are clearly stated, right? These numbers L and W and E are assumptions that are made about the underlying platform. Every engineered system makes assumptions about the underlying platform. You cannot deploy a system that will execute correctly always, right? It will only execute correctly under certain assumptions. A simple piece of imperative C code will execute correctly if the microprocessor hasn't overheated, if the microprocessor still has power. There's assumptions. Usually these assumptions go unstated. Here the assumptions are very clearly stated, and more interestingly, violations of the assumptions are detectable at runtime. If Seattle has issued a reply to this message with timestamp R, and it later sees a message with timestamp T less than R, it knows, Seattle now knows, or Dallas now knows, that one of the assumptions was violated. It will treat that as a fault condition, okay? That's not part of the programming language semantics. It's a fault detection schema. Something went wrong in the system, and one of my assumptions was violated, and I can no longer guarantee correct behavior. I have to handle it as a fault. Okay, so this ability to detect faults based on clearly stated assumptions is an extremely nice property of this model. Now, we introduced this model, I believe it was the first introduction of this model, although, it's really quite rare for things to ever be first. The people who usually get credit for an invention are the last people to be the first ones to describe it. As far as I know, we are the last people to be the first to describe it, but I'd be interested in knowing if there was prior work that had this. But we introduced it in a paper in 2007, and we called the programming model TIDES, and our application was cyber-physical systems, not databases. It was fascinating to me when Google introduced this for databases because it never occurred to me to apply it to that context. So what is the cost of this? Well, usually people latch on to the synchronized clocks requirement. But the fact is that synchronized clocks they're already kind of ubiquitous, and they're becoming much more so, and they're becoming much more precise. And as soon as people recognize the value of having precise clock synchronization, it's going to get much more prevalent. This particular picture is from the Berkeley campus, and it shows two horribly unsynchronized clocks. But the fact is that every laptop that you have today synchronizes its clocks using NTP, and NTP is not very precise, but it's better than a second. You can pretty safely assume that any two laptops in the room in Kiel agree on the current time of day to within a second or so. But there are much more precise technologies available, and the technology that Google uses in Spanner assures clock synchronization on the order of tens of nanoseconds across the data centers, and it's not very expensive technology to deploy, and it's widely supported by networking infrastructure today. The second thing is the assumption on bounded network latency. But the fact is that anytime you have a real-time system, anytime you have to issue a reply in real time, and that reply may depend on things coming in over the network, you have to make an assumption about bounded network latency. The problem is that many times in real-time system design, these assumptions are made but not explicitly. They're just somehow part of the background, and then you test the system to see if somehow it always works. And what always works ultimately means is that messages were delivered on time. But this schema turns that problem around and says, actually, I'm going to make this assumption very explicit, and I'm going to give you a mechanism for detecting violations of the assumption. And in fact, it forces you to make the assumption explicit, which to me is a tremendous advantage of the schema. We also have to assume bounded execution times, but this is very common assumption in real-time systems, and it's a thorn in the side of real-time system designers. This is actually solvable in a very rigorous way using precision time machines, but that would be an entirely different talk. So we can just assume that we'll handle this in the usual way for real-time systems, which is to do worst-case execution time analysis. So what can be verified using this approach? Well, actually, let me skip over this in the interest of time. So the principle here is that we're using a model of computation where designing the software that satisfies the properties of interest is easy, right? Think of the door controller for the aircraft. If it receives a timestamp message to open the door, the infrastructure guarantees that under these clearly stated assumptions, it will not later receive a message with an earlier timestamp to disarm the door. Then the software design is trivial. You receive a message to open the door, you open the door, period, right? A trivial problem has a trivial solution at the application level. That's the way it should be. Implementing it, of course, requires more work. You have to implement the clock synchronization schema. You have to ensure the network latency, perhaps using time-sensitive networking technology, for example, evolving Ethernet standard. And the work gets done here in the infrastructure, and that's the hard part. But that's application independent, right? That gets done once to provide a whole framework within which many applications can be designed. And this is following the principle to keep the hard stuff out of the application logic, put it into the infrastructure instead of in the application logic. So today, this was 2007 when we introduced this, and we did build an implementation of this. We built a bare iron operating system that could run this TIDES model on a distributed system. It was called TidyOS, and it was meant for being deployed in deeply embedded systems, in factory automation systems and the like. But today we're taking a much more, I think, broadly applicable approach, and we're developing this language that we call lingua franca, which is a polyglot meta language. It's not really a programming language, but it's a framework within which you build programs that are potentially distributed, potentially concurrent, that use this, what Stephen Edwards calls the sparse synchronous model, what people have traditionally called discrete event models. So the way that these work, in lingua franca, the components are called reactors. I like to think of that as actors revisited, because they're a bit different from the Hewitt actors. They're much more deterministic, and they're different in certain key ways. One is that instead of having a single message queue into which messages arrive and they get handled in FIFO order, The reactors have input and output ports, and then they can be composed by connecting these ports together, and that gives us message channels, which we can now exploit properties like in-order delivery along a message channel. If that's guaranteed by the network fabric, that's something that we can take advantage of. So an application sketch that looks kind of like what the aircraft door example would look like. We have some sensors scattered in various places in your network. You have some computation scattered in various places in your network, and you have places in the network where things come together. And the key thing is when they come together, there will be timestamps that define the order in which things can happen. And then you have actuators that take time-stamped events and then have side effects in the physical world. So in this application sketch, the way it would look like in lingua franca is that each of these components would be a reactor. So a simple one is this computation, and the computation has time-stamped inputs, and the port is named X, and it has time-stamped outputs, and a requirement in lingua franca is that outputs that are produced by a reaction to an input have the same timestamp as the input. So they're logically instantaneous. This is a property that we borrowed from synchronous languages, and it inherits, lingua franca as a consequence, inherits the very nice determinism properties of synchronous programs. It can have local state. That state is not visible to other reactors in the system, and consequently there can be a guaranteed lack of interference between these states, and that is part of what enables concurrent and distributed execution. The reaction signature gives the inputs that the reaction depends on and the outputs that it may produce. And the body of the language, the body of the reaction, however, is in target language code. So this is not part of lingua franca. In fact, currently lingua franca supports writing the reaction code in C, C++, TypeScript, which is a type-safe version of JavaScript, and Python. The body of the reaction can reference the input ports and produce data on the output ports, but this is arbitrary target language that the lingua franca code generator doesn't even look at that code. Determinism looks like this. If you have a computation that has two input ports, then you are assured that this reactor will be triggered in timestamp order. Now, there is a possibility for, at a particular logical time, for there to be inputs present on both of these input ports. So you could get a disarm message at the same logical time as a open door message. So that would occur, for example, if the cockpit had a switch that said disarm and open, okay, and then it would issue disarm and open and assign them the same timestamp. And as a consequence, those will be logically simultaneous, and they will both be present when this reaction is invoked. So in the C syntax, with the C target, this is C code. This is what it looks like. You just say you want to sum the two inputs, okay? Then you check to see if the first input is present. You add to the result. If you check to see if the second input is present, you add to the result, and then you send the result on the output. Okay, and this is done in C code that the lingua franca compiler doesn't even look at this code. So whether two triggers are present simultaneously depends only on their timestamps and not on when they are received nor where in the network they are sent from. Lingua franca explicitly has explicit support for time. Time is a first-class data type. In fact, it's actually the only data type in lingua franca. All other data types are simply the data types of the target language. So if you have a language like C with a very weak type system, then the lingua franca programs that you construct with the C target will have a weak type system. You won't get much in the way of type guarantees. But if you use a stronger type system like TypeScript, then you will get much better properties. Okay, so this is the polyglot nature of the language. But you can specify things like here is a timer that is specified that will begin ticking 1 millisecond after the starting point of execution, and then will tick every 100 microseconds. And then you can have a reaction to this timer that produces output Y, and this might, for example, poll a sensor. So if you have a sensor that you want to poll every 100 microseconds, you can poll it here. And you're guaranteed that if anywhere else in the network there is a similar timer, then the results of this polling will always be logically simultaneous to whatever that timer produces. wherever in the network it is. Okay, this is a logical notion of time, and this logical notion of simultaneity is a very strong property of the language. In the C target, timestamps are 64-bit integers that represent the number of nanoseconds since January 1st, 1970, if your platform has a real-time clock. But we've also deployed this on platforms that have no operating system, and therefore they don't necessarily have a real-time clock. And in that case, it's common to just use the number of nanoseconds since the reboot of the system as your timestamp. You can have event-triggered behavior. So we can have a sensor that is not polled and not time-driven, but is rather event-driven. And the way the lingua franca code looks for this is we have a notion of a physical action. And Martin Lostra, I think, talked about this earlier today. And this, to me, is one of the most interesting aspects of lingua franca, because I mentioned briefly that the emphasis in Martin's talk was on the multiplicity of timelines, the fact that every platform has its own measurement of physical time, and that there's a logical notion of time that is overlaid on top of that. And the physical actions acquire their timestamp from the local physical clock. So the way that this works in lingua franca is in a startup reaction. Say this could be done for a bare iron machine, right? So this will generate C code that runs on a microcontroller that sets up an interrupt service routine that calls a library function to schedule the action A. And the library function here will assign it the timestamp based on the local real-time clock. And then you define a piece of reaction code to that action, and that reaction code can produce the logically timestamped output. So that's what the code looks like in lingua franca. So timestamp will be, in this case, derived from the physical clock. The interrupt service routine can execute completely asynchronously, and the schedule function is thread safe in this case. So lingua franca reactions can be executing at the time that schedule executes, and you're still going to be guaranteed that events will be processed in timestamp order. You can also bridge logical and physical timelines using deadlines. So deadlines are subtle, and I think Martin talked about them already this morning, but they relate physical and logical time, so I'll skip over them here because I don't want to get too redundant. So this project is still early, but we have a GitHub repo and a few examples and quite a few regression tests for language features that you can look at. Now, one of the things that I would like to emphasize is when I started this project, I was very worried about the performance that we would get, because I have a lot of experience with discrete event simulators, and they can be dogs in performance. They can be very slow. And I was concerned that an explicitly distributed discrete event and a concurrent implementation of discrete event simulation would be costly. I've been proven wrong, and I have to really credit one of many design decisions that Martin Lostra came up with, which is it's a dual queue schema. We don't, instead of using a single event queue for everything, there's a separate queue that handles each tick of the synchronous clock, and that is separate from the event queue. And this tremendously reduces the load on the priority queue that implements the event queue, and it gives us tremendously good performance. So just to give you some numbers, running on my own Mac OS laptop, which has an 8-core CPU, I can get up to 28 million reactions per second on each of 8 cores if I have enough parallelism in my application. So it's much lower overhead than I ever imagined was possible. So I've mentioned clock synchronization. I don't want to go into this in detail because it's a long topic, but I'm convinced this will become ubiquitous at high precision. So there's a lot of questions that lingua franca opens up, many of which we haven't answered. I mean, one that I think we do answer is, how do we get repeatable and testable behavior even when communication is across networks? And how do we specify, ensure, and enforce deadlines? A question that we have not really answered, but that is a natural consequence of the language, is what combinations of periodic, sporadic behaviors are feasible? There's low-hanging fruit for applications, for example, of network calculus to answer these questions. And how do execution times affect feasibility, and how can we know the execution times? And of course, assuming correct execution, does the program meet the spec? So there's lots of opportunities for verification on this program. So in conclusion, lingua franca programs are testable. This is a key property. You can define test vectors, which are the sets of time-stamped inputs, and a correct execution of the lingua franca program will give you a deterministic result. So you now can map this onto a regression test scheme, right? You check your implementation for this test vector. Does it give you this result? If you don't have a well-defined result, then it's very hard to write such regression tests, right? Your regression tests have to tolerate all possible results, and that may be a very large number of results, as it would be in pub/sub or actors or service-oriented architectures. So lingua franca programs are deterministic under clearly stated assumptions, and violations of the assumptions are detectable at runtime. And actors and publish and subscribe and service-oriented architectures and shared memory architectures have none of these properties. So thank you very much, and I will stop there.